Ideal flow. In this lesson, we are focusing on the continuity equation and the stream function. First, we are focusing on the continuity flow in Cartesian coordinate. Let's say we have a particle or control volume like this. So mass flow rate into the element of x and y direction is shown in this figure. So to analyze the continuity flow here, we imagine that we have one inlet in x direction and we have one outlet in x direction. At the same time, we will have one inlet for y direction and one outlet for x direction, like this. The net flux of mass entering the element equal to the rate of change of the mass of the element, and this can be simplified as this one. We could write as m dot as mass flow rate at inlet minus m dot mass flow rate at outlet is equal to d dt of the mass in the element in the control volume. So means the changes of mass in terms of time in the control volume. We could calculate the value of m dot here, mass flow rate, by using this equation, rho, A, and V, which is rho here is the density of the fluid, A is the cross-section of the inlet or outlet, and V is the velocity of the fluid. And mass here can be calculated by using this equation, rho times volume. And the volume is referred to the volume of fluid. What we need to do is, based on this diagram, we need to fulfill this equation. For example, we start with m dot for inlet. Mass for inlet is, we start from here, for example. We have inlet in x direction. It can be calculated as rho u dy dz. To calculate the m dot or mass flow rate, we use this equation, rho AV. So we have rho here. We have A is dy dz, means we multiply the height of dy here and we multiply the width, which is dz. And we have v, the velocity here, because it is moving in x direction, so we take the velocity at this point is small u. So rho u dy dz is the mass flow rate for the inlet. And mass flow rate for inlet for y direction here can be written as rho v dx dz, as shown here. Rho is the density, dx dz is the cross-sectional for this area. We have dx here and times with dz to get the cross-sectional area, A, and the velocity at this inlet is component velocity of y, which is small v. So this is the mass flow rate for inlet for x direction. This is the mass flow rate for inlet for y direction. Then we substitute the value of mass flow rate at the outlet. So this is the mass flow rate at the outlet for x direction. We could write as rho u plus del rho u over del x dx dy dz. So here, dy dz here is the cross-sectional area. So because our element here is a square or a symmetrical control volume, so the cross-section area is same with this one, dy dz. However, for rho and velocity here, for the first, we are advised to write this term in terms of partial derivation. So we learned about partial derivation for this one in previous lesson. So we could write as rho u plus del rho u over dx here as the outlet, the mass flow rate at outlet for x direction, and for mass flow rate at outlet for y direction can be written as this one. So we write as rho v plus del rho v over del y dy dx dz. And then we write the mathematical equation for del dt mass for the element. We know that mass can be calculated by multiplying rho and the volume. So we have rho here, and the volume of this control volume is dx, dy, and dz. So we write as del over del t, rho, dx, dy, and dz. Then we, simplifying the above expression, we could write as del rho u del x plus del rho v del y plus del rho over del t equal to 0. And if we calculating in three-dimensional, we could add the value of z direction, and the terms here will become like this: del rho u del x plus del rho v del y plus del rho w del z plus del rho del t equal to 0. And then if we expand this term, we could write like this. And this is the most general form of the differential continuity equation expressed using rectangular coordinates. For the case of incompressible flow, a flow in which density of a fluid particle does not change as it travels along, the continuity equation can be written as follows. It's become del u over del x plus del v over del y plus del w over del z equal to 0. Please bear in mind that in incompressible flow, the value of density is remain constant. So we could simplify the value of density, and we could have the simple terms of continuity equation like this. Assume that we are only discussing two-dimensional coordinate and there is no changes in density, which is incompressible flow. We might express the continuity equation as follows. So we neglect the value of z here. We could have del u over del x plus del v over del y equal to 0. And because it is not a partial derivation anymore, we could change our continuity equation here into du over dx plus dv over dy equal to 0. Please bear in mind that in continuity equation, your value must be equal to 0. If not, it means that the continuity equation is not fulfilled. So it means that your equation later on is not correct. Please remember that continuity equation must always equal to 0. And this is the continuity flow in polar coordinates. So again, the detail for this one is already taught in a previous lesson. So this is the representative element for polar coordinates. So we have this one. It is, if we extend this line, it actually comes from origin or the axis of the circular motion. So the angle here can be denoted as d theta, and then the length here is dr, because this is the r axis, and we could calculate the length of this one is by equation of r d theta. And for this curve, for this length, we could calculate as r plus dr, because we have r here until this point, and we need to add dr to express the total value of radius at this point. So we write r plus dr times d theta. So the angle here is not changed. Please do not make mistake about the angle here. So again, we have two input and two output here. So the inlet for the inlet is here and here. So this is represent for the radial axis, and this is for the angular axis, and this is output for the angle axis, and this is the output for the angular axis. The net flux of mass entering the element equal to the rate of change of the mass of the element. And to simplify our calculation, we assume that z direction in this situation is equal to 1 unit. Again, we will use the same idea of like previous calculation. We use the idea of mass flow rate at inlet minus mass flow rate at outlet is equal to changes of mass in the element in terms of time. So we could write as del dt for the mass element here. So to simplify this calculation, I calculate it separately. So first we calculate the mass flow rate for inlet. So we have here Ru Rd theta. Again, we could calculate the mass flow rate by using the idea of rho A and V. So Rd theta is the distance of this curve, and we multiply with 1, so we get the cross-sectional area. And U here is the component velocity for the radial, and rho is the density. And another inlet is here, rho v dr. So again, dr is the distance of this one. We multiply with 1, the z-axis, so we still get dr, and v is the velocity component for the angular direction here. So we have rho v dr. And the outlet here, so this is the outlet for the radial axis, and this is the outlet of the angular axis, and the detail for this one is already given in previous lesson in chapter 1, the differential method, the differential form of the fundamental laws. So we use the differential method here. So we have the mass flow rate at outlet is rho u plus del rho u d over dr dr, r plus dr d theta plus, and this is the mass flow rate for the angular direction, rho v plus del rho v over del theta d theta dr. So dr here is the cross-sectional area, because dr is the length of this one, and the width is equal to 1. So, and r plus dr d theta is the length of this one, and we multiply with 1 because the z value is equal to 1. Then we calculate the del t for the mass for this element. So because this element is quite not the length here is not same, to simplify this calculation, it is okay for us to take the volume for this one is rho r d theta dr. R d theta is the length of this one, and dr is the distance of this one, and it is okay for us to multiply these two lengths and multiply with 1 to calculate the volume of this element. It might be a little bit simplification calculation to get the volume for this element. Then the equation can be written as this one. So we expand this equation, and we assume that, for example, if you have dr times this dr, the value of dr times dr is too small, and we could neglect the value. So finally, after we expand these terms, we could get the final term as this one. I hope you could try this at home, and I believe that you could do. You can do it. And please be careful when you try to expand this in terms of partial derivation. So this is the simplification, we simplified this term into these terms, and then we divide all that term with dr, d theta, and r, and finally we could have this one. And this is the official or the common continuity equation for polar coordinates. So it's del rho over del t plus rho u over r plus del rho u over del r plus 1 over r del rho v over del theta is equal to 0. Please bear in mind again, please remember that continuity equation must be equal to 0. And for these topics, we are focusing for incompressible flow, means that the value of density is constant. So this equation can be simplified as u over r plus del u over del r plus 1 over r del v over del theta equal to 0. Then, because the term del can be changed into the normal differential, so officially in this topic we will use the continuity equation for incompressible flow in polar coordinate can be written as this one: ur over r plus dur over dr plus 1 over r du theta over d theta equal to 0. So here I change the value for u and v into ur and u theta. So normally, if you could see this slide, u will be changed into ur, means the velocity at r direction, and v here is changed into u theta, means velocity at angular direction.